Welcome everyone. In this video I'm going to show you how we can recycle the stepper motors from floppy drives and how we can run and use them. So as you can see, there are a lot of things on the table, but first of all let's look at the floppy drives. So I got these drives recently, two of them, they are the same, and here is our target stepper motor with 4 connections. And what I try to do is I try to disassemble this whole thing and remove the mechanism together with the stepper motor, and then I want to show you how you can wire up the stepper motor and drive it with a microcontroller using some stepper motor drivers and some rotary encoders and of course the axle stepper library. So everything is Arduino based here, and basically that's all. So this is the motor part and the salvaging part. We will need a multimeter just to measure the polarity of the motor, and then I have these things here. So 2 independent rotary encoders. Later on I will talk about them because they are some new stuff I discovered on the internet. Just an LCD to show the amount of clicks I do when I rotate the stepper motor or rotate the rotary encoder, and also the amount of clicks, because this is also a button as you can hear it. Then the microcontroller, again an STM32 blue pill, and then I have these boards which are just some breakout boards, as you can see, for DRV8825 type drivers. So it goes in like this. You can change the microstepping with these dip switches. This is the output for the motor, and then you have a 5-volt logical input. So that's the 5-volt coming from the microcontroller, the ground, which has to be wired to the microcontroller and to the power supply as well. So the ground is common. And then you have a 9-volt input. This text here suggests you to use 9-volt 1 ampere power. But I guess we can go higher. We can check it on the capacitor that is 50 volts. So I guess nothing hinders us to go higher. I will check it. I haven't checked it yet because I just unboxed this. And then here we have E, D, and S, which is enable. And then we have the direction and we have the step pins. So in principle, we just need to have 2 control pins, step and direction, which will be defined on the microcontroller, and then enable is usually either pulled to ground or to high level. It depends on what you want and how the logic is wired with this. We will see. And technically that's all. So in the first part I will disassemble this, and some parts will be like speeded up. And when I want to talk about something, then I slow down the video and I will talk about the certain parts. And then the second part of the video will be to show this in action, and the third part is to show you how this code works. And of course I will share all the wiring and everything, but for that check the description down here. You will find some links leading you to my website, and you will see the coding for this thing and also the wiring and all other resources if there is any. So I just clean up here and start disassembling the units. So there is a bunch of screws on this PCB and on this metal panel. So I will just remove everything one by one. So this is an electric motor, and this drives the inside of the floppy disk. And as I don't really need this kind of tape, I will destroy it by just cutting it. So I can remove this from here. Since I don't need the parts of this drive, it's fine to cut it. But there are a few pins here, which I guess go to this controller, and then they continue their way to the motor. So I had to cut a few cables. Two of them are coming, I guess, from the reading head. And then another cable goes to somewhere else. And then the most important cable, which I cut here, is the cable, the 4 cables for the stepper motor. So now you can see that this ribbon is free, but I will actually remove this whole thing and I will solder my own cables over this thing. My camera unfortunately doesn't have autofocus, so this is what you get. And I also saw some bugs from this drive coming out from this drive. So I was right about those 2 cables. These are the cables which are going to the reading head of the disc, but I don't need that. But now you can see the mechanism for the stepper motor. So I will try to remove this plate. So this is one of the heads. The other is there. Then here is the stepper motor. So this is one of the steppers. It still moves. I can feel a little bit of resistance, but it's here. So now the question is that how is the wiring? So if I go back to the PCB and check how I cut this, I can see the polarity, sort of, because there is a number 1 here, so I guess that belongs to the first pin or first connection. Nevertheless, we can do this in the other way. We just need a multimeter, and then we put it in continuity mode, and we have to make sure that it beeps. So now there are 2 coils in this device, so we have to look for those coils, and all you have to do is you check one pin and you check the others with it together, and then try to see when it is shorted. So the first one from this side, I try to show it closer. So the first pin is in connection with the middle pin. So then the second should be in connection with the last one, but let's check it also. So second one, and it beeps. So yeah, basically every second is connected, or depends on how we look at it. So I will just cut this short, and then I will remove most of these foils and just add my own wire to this. But if we come back to this box, there is still a few parts left which would be important for us. For example, this mechanism, which sort of grabs into the threading of this thing, and then with that it acts as a sort of a nut. So when this thread rotates, then this carriage will move up and down. But unfortunately this thing is pressed together in a stupid way, stupid for me, because I cannot really disassemble it without destroying it. that I cannot really move forward in disassembling this thing. So I just put this aside and we'll just focus on removing the other motor from the other similar floppy drive. Then I will solder the wires and assemble everything and test it. And later on we can just use a piece of solid wire and just sort of drive against the threads, and that should be enough to just move something very light over this threading. So let's just disassemble this other drive. So we have two identical tiny stepper motors, as you can see. So now I will do the soldering part and try to make them move. So this is done. I have to check if I made any kind of short circuit, but I think not. Yeah, it looks alright. So the identical colors are, they belong to the same coil. So blue is one coil and then red is another coil. So I will repeat the same exercise for the other motor and then we will move forward. And I will make the connectors for this white connection, and finally we can test it with the Arduino. This one is also done, and I see no short circuits. So now we have to prepare the connectors. So for this exercise we will need a crimping tool and of course the connectors. So once again I just show you what is at the end of this circuit. So 4-pin connector, and then this is the counterpart. It will go in like this, but I have to prepare the cables for this. So we have these metal rods, quite a lot of them. We need 8, 4 for each. So this should be 8. That's all. 2 of this. So here it's before wiring, it's really important to know how the output is located on the board or on this driver, and you can see that there is like coming from the top 2B, 2A, 1A, 1B. So you have the outputs going to one single coil next to each other, but here the coils or the connections for the coils are not next to each other. But that's why I used sort of a color coding. So I use the similar color for the same coil, so you cannot mix it up really. But this is just something you have to keep in mind when you wire everything up. And then of course here on the PCB, if it's not shining too much, you can see how the wires go. So actually they just go in the same order, as you can see the numbers here. So when you have the 2B, that's here is the bottom, and then 2A, that's the next one, and then you have 1A, 1B. So that's the order. So we will follow it here. So now I just cut this up and then remove some wire, strip it off, put this on the wires with the crimping tool, and it's done. So of course it's not visible because of the bad focusing, but the first part of this metal thing, which you can see that large V shape, that hugs the plastic cover, or in this case it's a silicone cover, and then the inner one, which is much shorter, that grabs or crimps the metal wire. So that's how it should be done. I actually have a video on this, how to make this connection solid. Check the corner up there on the right top corner, and you will see this in a much better quality. I used some macro lens and other stuff to make this process more visible, and I explained it in a detailed way. So one is assembled, just to test if it works. I mean, just the physical connection works. Just try to plug it in. Seems solid, nothing is falling apart. So I just do the same exercise for the other. Yeah, it stays in one piece, so it's fine. So I just do the same for the other. So the motors are wired up. I just clean up this thing a little bit because there are too many pieces over there. And after that I wire up everything and we go to the microcontroller part. So finally everything is assembled. So let's just quickly go through the parts. So the brain here is an STM32 blue pill. This is the microcontroller, which is then connected to two individual stepper motor drivers, and then they go to the stepper motors. The stepper motor drivers are powered through these clips from a laboratory power supply. Then on the right side we have two rotary encoders, and they are amazing because they come in a PCB, so they are already soldered in a PCB with the 5 pins which we need, and it comes with a cap. But what is more important is that here we have the wall debouncing circuit for the switch and the two output pins of the rotary encoder. So that's quite amazing. I really like this. And then finally here we have the display, and of course now as I place this thing back, it picked up some signals, so we have different numbers. But what we see on the display is in the first line we register the things for the left hand side rotary encoder. So if I move this, of course the number increases or decreases depending on the direction, and if I click, then I increase the number here. This is just some demonstration. And also if I do the same with the right hand side, then that goes either up or goes down, and then also I can play around with the button clicks. And then finally I have a thermometer here, which is a K-type thermocouple thermometer, because these things can run quite hot and I want to test how hot they can run. So all I have to do is I power on this thing and see what is happening. So they are powered now, and I move this now and you see the flag, the small electrical tape, and it's rotating. And now I move this. So it's wired in the opposite way, seems like. and then it moves. And here, this is the most shocking part, or the worst thing. Now I try to push it against that. The temperature of this thing is running quite hot, and I can barely hold it. So I try to use some tool. So as you can see, this is now 83 degrees. So I cannot really touch it because it's so hot. And now I can start to smell it as well. So this is a big problem. So I turn this off. So as you can see, these are running quite hot, which is not necessarily good for us. So the problem here can be is that the driver is putting too much power out on these poor motors. So there should be a solution for this. And for that, I will test another stepper motor driver which should deliver much less power, and therefore they can stay cooler. So let's test that. So I rewired everything and I installed the EasyDriver circuit for this motor. And then for this I kept it the same, and I tried to put the current to the minimum by adjusting the potentiometer here. So I just reset the microcontroller just to reset the numbers. And then I will turn on the power supply and see how the two temperatures develop. So now power is on, and I grab this. That's an easy check. So as you can see, I can move it easily, and I can hold it in my hand, and this is still okay, but it's getting hot. So let's try to measure it safely. So as you can see, the temperature of this thing is getting very hot. So that's like almost frying. So I just removed this from the power supply. There we go. And then we have this. So notice that I can still keep it in, hold it in my hand, and it works. And the temperature is just body temperature. So maybe this is my fingers temperature. So this works very well. And it's 40 degrees, whatever. That's manageable. As you can see, I can hold it in my hand, but I pretty much believe that I should not really touch this. And I was right, this is hot. What I try to say with this is that this driver is just simply delivers too much power for this tiny stepper motor. And some of you might have experienced quite high temperatures with these drivers and with these stepper motors. However, if you switch to the EasyDriver, this is still running, and I haven't disabled the power and anything, and as you can see, it's moving. So this, I can still hold it in my hand, and it has a manageable temperature. It's exactly 40 degrees, so this is nothing. So this works well. So the conclusion of this is that if you have a stepper motor in this kind of size, which is, for example, coming from a floppy drive, you should use it with the EasyDriver with the minimum current, because then you can use it on a long run and move it and whatever, and it will not overheat. However, if you are using it with the DRV8825, so this kind of driver, or even more powerful drivers like the TB6600, for example, you will kill this motor, because the internals will just simply melt. They have a very delicate wiring inside, so you don't want to run too much power through it, because the enamel on the surface of the wire will melt, and then you will short out the wires, and it will just destroy the whole circuit. But this is fine. I mean, I'm grabbing this and nothing happens to my fingers, and it still works properly. Now the microstepping is at the lowest one, so it is what it is right now. I haven't stepped it, but this is more than enough for me. So yeah, the conclusion is just, again, you can use this EasyDriver to run these kind of stepper motors, and you don't have any problems with them. At least I don't experience anything but if you use the DRV type, it will be very hot. I still cannot touch it for a long time. So yeah, this was all. And what I'm going to do now is I will show the code on this microcontroller. So I will go to my computer and go through the coding, but there is nothing extraordinary. We are just moving these two knobs, and then you increase these numbers, and these numbers are used as the absolute position of the shaft of the stepper motor, so they will move always to that absolute position. So now if I move one direction, then it goes there, but if I move backwards, of course then it moves backwards, because that's the next absolute position for this shaft. So let's go to the computer and let's see what is on the microcontroller. So this is the Arduino code. This is nothing else, just controlling code for the stepper motor via the rotary encoder. And in fact, almost every line is duplicated, so I just copy pasted a code which was already existing and already presented in one of my previous videos. And then I just doubled that code. So we need the exo stepper library. So as you can see, there are two instances of it, and then I called one of it as stepper 1, that will control one of our motor, and then stepper 2, which will control the other motor. So as you could see, I was able to independently control the two stepper motors with two independent rotary encoders, and this is one of the steps that I had to make in order to be able to do that. And then we have the LCD. So I'm just including the typical library for this liquid crystal I2C, and then we have a 16:2 LCD at this address. So this is what we have, and whenever we want to change anything on the LCD screen, we will call for this LCD. And then we have a bunch of pins, and those are defined down here. So we have 3 pins for one of the rotary encoder, and these pins are the switch, the CLK, and the DT. And then the same is for the other rotary encoder, of course, assigned for different pins on the microcontroller. And then I need some variables to store the number of clicks done with the rotation of the encoder and the number of clicks done by pressing the button on the rotary encoder. So then we have one rotary encoder, which will be indicated by the number 1 at the end of the name, and then we have another rotary encoder, and we store the same numbers, but this belongs to another rotary encoder, so I use the number 2. And then we have a bunch of variables for the statuses. So we need to keep track of the DT and the CLK pin and their previous statuses. So we can always compare the current status with the previous status, and this will tell us the direction of the rotation. So these are just listed here. And finally, I will measure the time in 2 different or 3 different occasions or scenarios. So one will be for updating the LCD, and 2 is a sort of a debouncing for the buttons. You will see it later. And in the setup, we initialize the LCD, and then we put the cursor in the top left corner, so in the very first block in the left corner of it, and then we print this text, and then we jump to the next line, but in the first block of it, and then we just again print something. And since this is a 16:2 LCD, there are 16 blocks available for printing, so you can print 16 characters, and there are 2 lines for this. And then I wait a little bit, and this message therefore will stay on the screen for 5 seconds, and then we do these definitions for the pins. So I turn on the input pull-up resistor for all pins. However, we have the pull-up resistors and the debouncing circuit on the circuit of the rotary encoder already, but let's do it extra safe by doing this, and this doesn't really have any negative effect if we already have the circuit. So then I just define all the pins, and then I distinguish between encoder 1 and encoder 2, so I can follow everything in the code. That's relatively easy. And then we read the statuses of the CRK and DT pins. So these will be the initial statuses. So when the code runs, so we actually left this setup part of the code, and we start to rotate the encoder, the next status of the encoder will be compared to these statuses which we read right here. And then we will use the interrupt function for the rotation, but only on one pin of each rotary encoder. So this is defined for the CRK1 and CRK2 pins. So these are two independent rotary encoders, and then they have the same function, but one is called rotate1 and the other called rotate2. And we are looking for a change. So that means that if there is a square wave, we also look for, not only look for the rising edge of the square wave, but also for the falling edge. Then these are just some random numbers, or nearly random numbers, for the speed and acceleration values of the stepper motor. But since we go step by step, these numbers are not really relevant. We start the timer for the time now variable, and we just read the millis right now, and then we print everything on the LCD. And finally we arrive to the loop. So this set of functions will run endlessly. So every 100 milliseconds we print the LCD. So what happens here is that we calculate the elapsed time. So the time elapsed between this part here and the time right now when we enter this if condition. And if that number is larger than 100, then 100 milliseconds is gone, elapsed. So then we enter, and then we print the contents to the LCD display, and we sort of reset the timer. So now we read the millis again. So if we would read it again very quickly, let's say no time is elapsed between the two readings, then this will be 0. And then again some time elapses, and then this will be a larger and larger number, and always larger than this. So we will approach 100, and that's how this kind of timing works. And then we keep track of the buttons, whether they are pressed. So there is no interrupt for the buttons. We are just running the loop very quickly, and then we are just checking for the status change of the button. So this is a very simple reading status. And then there are two functions to run the motors independently. Here, this is the print LCD, and this is for one part or one motor, and this is for another motor. I just go through this part because everything else is the same. So what happens here is that we put the cursor in the top left corner, so the very first block of the two-line LCD, and then we print R1. And as you can see, this takes up 4 places. And then we move to the number 4, which is the fifth block of the LCD. And then we print 4 spaces or white spaces. And that will erase the numbers in those 4 blocks, if there is any. And then we move back there to the beginning. So basically we put the cursor here where you see it blinking right here. And then after this is done, so the cursor is moved to this part, we print the variable into that block. And then we move to the 9th block, because we start the now counting from 0. And then we print B1, which will be for the button 1. And then we move to the 13th block. So essentially here we erase the following parts. We move back to the beginning, so the cursor will be here where it can be seen blinking. And then we print the number of clicks, which is the value of the button counter. And then the same is done in the second line. So exactly the same, but this is for the encoder number 2. So now you can see how we run the motor. So what we do is we always follow the absolute values. So we use the move to function in the axle stepper library, and here we instruct the stepper motor 1 to move to the value of the rotate counter 1. So if the rotate counter 1 value is 400, then the stepper motor will be 400 steps away from the original position when you started the microcontroller. And then if the rotate counter is minus 400, then it will be again 400 steps away from the original step, but in the other direction. So if you have the, let's say, positive convention of the rotation, then this thing at minus 400 did 400 steps counterclockwise. So this is how it works. And what it does here is, this is sort of a blocking operation. So when there is a new instruction, it checks if there is a steps to go. So this is what this distance to go function does. So it checks how many steps has to be done from the current position of the stepper motor. And if this number is larger than 0 or not 0, then the stepper motor is instructed to run to that new position. So this will run until this value will not be 0. That means that the stepper motor is moved to the requested position. And technically the same happens here, but with the other motor. So now we jump to the function which takes care of the rotary encoders. So what we do here is we read the CRK again. So if you remember, we read it once in the setup. So this is read again, and it is compared to the setup's reading. So this is the CRK now 1 is basically compared to the CRK previous, and also there is another condition that it should be 1. And if it's 1, then if this wall condition is true, then we enter here, and now we compare the current value of the DT with the current value of the CRK. And based on the outcome of this condition, either we increase the value of the rotate counter variable, or we decrease it. And then finally what we do is we save the current value of the CRK pin of the rotary encoder as the previous value. So this will be compared to the new reading in the next click whenever this function will be called by the attach interrupt. And then the same happens inside this. So this is exactly the same, but it is for the other rotary encoder. And finally we have the buttons. This is very simple. So this function runs every time when there is a iteration in the loop, in the main loop. So then we check if the PB1, which is the switch pin of the rotary encoder, if this is 0. And sometimes it should be 1, because it depends on how you wire the rotary encoder. And in this case, this should be 0. So when this condition is fulfilled, and there is at least 300 milliseconds elapsed from the last time when we triggered this function, then we increase the number of the button counter, or we increase the value of it, and then we reset the timer. So this means that if you press the button twice very fast within 300 milliseconds, you won't register multiple clicks, just one. So you always have to wait 300 milliseconds between each clicks. And this makes it sort of a foolproof or fail-proof, more like, that you cannot register multiple clicks by pressing the button once, because some buttons tend to ring or bounce, and therefore this function will be triggered several times if we don't have this delay, sort of delay. And that's why I haven't put a delay here, because that would block the main loop. but I just put a sort of a timer here. So we just check inside this function at every 300 milliseconds instead of waiting 300 milliseconds and blocking the other parts of the loop. And the button pressed function, of course, does the same. There is nothing extraordinary. It is just defined for the other pin, which is assigned to the switch pin of the rotary encoder. So you can see that this is an extremely easy task and quite simple set of instructions inside this thing. So once again, this runs endlessly, and then basically these two functions are the most important. So they check whether there is a step has to be done on the stepper motor controller or not. And if there is something, then the microcontroller sends out the pulses to the controller, and then the controller will move the stepper motor to the requested position. And then based on this, you can set up a lot of things. It's just, yeah, it depends on your fantasy. So I hope you learned something from this video. I try to show you how the different drivers can run the stepper motors, and once again you have to be very careful about picking the correct driver for these very sensitive stepper motors, because they cannot run at too high current or voltage, otherwise they will just burn, as we could almost see it in my case, because one of the driver was too powerful, and that ran the motor to 100 degrees Celsius or over 100 degrees Celsius temperatures, and I could not touch the stepper motor at all. However, if I picked a more weaker driver, which is more suitable for this kind of stepper motor, the temperature was around 40 degrees, which is quite okay for touching it by hand and also for the lifetime of the stepper motor. So this was a really simple instruction, but I think it can be useful for those who try to use or recycle the stepper motors from floppy drivers, and the same applies for CD-ROMs or DVD-ROMs or whatever disk drivers or drives. So I think this was all about this topic. Don't forget to check my website and also check the description down under the video, because there are extra resources on my website, and I always put the link there, so you can find the wiring and the source code and everything there. I hope you learned something. I hope you found this video useful, and see you in the next video.